thermochemistry? Okay, we have a pretty good idea of what chemistry is. What is thermochemistry? Thermo means heat, right? I can remember this definition from grade school. What is energy? The capacity to do work or produce heat. And we're interested in chemical reactions that either generate heat or absorb heat from their surroundings. As a matter of fact, there are very few chemical reactions that do not produce a measurable amount of heat transfer, either into or out of. So most chemical reactions are eligible for this study. And we go back to the law of conservation of energy. Energy can be converted from one form to another, but it can't be created or destroyed. Another way of putting that is the total amount of energy, or the change in energy, for the universe. And I do mean the universe. I mean everything we know that exists. The total change of energy in the universe is 0. We just change it from one form to another. Now there's differences. There are differences among forms of energy as far as its usefulness goes. But we're not going to get deep into that until next semester if you come back. But we're going to introduce how scientists, chemists in particular, deal with transfers of energy. It's absolutely essential to understanding chemical reactions. This is also known as the first law of thermodynamics. Now, the thermochemistry is like a subset of thermodynamics. But historically, thermochemistry was investigated first, and then they saw that the issue was much bigger than that. It's much bigger than just chemistry. It includes any type of physical phenomenon. So you have, this is the first law, you have a second and a third law of thermodynamics. They even have a 0th law of thermodynamics. I guess they threw in the first, second, and third and says, uh-oh, what do we need another one, but it doesn't make sense to make it the 4th law because it precedes all the rest of them. So there you go. Okay, so there's the expression of the first law of thermodynamics, and it just means that conservation of energy, you can't create it, you can't destroy it. You can only change its form. So what are forms of energy? We can, spitball or just think about anything you want to. Just walk out on a sunny summer day, which I wish it was, and you receive energy from the sun. That's radiant energy. Or the temperature is warmer than it is now, and some of that energy is transferred to your body, and you feel warm. That's conductive energy. In fact, there are 3 ways of moving energy from one point to another. I don't know if I have a slide on this, but I'm going to put it here anyway. One is radiation. You can transfer energy from the sun anywhere in the universe simply by radiating the energy as light. Okay. That carries with it a certain amount of energy. If 2 objects are touching one another, you can transfer energy by conduction. Okay. Or if you just want to transfer bulk energy from one place to another, you can do it by convection. And just move the mass along with its energy to someplace else. Those are the 3 ways that we transfer energy from one place to another. Now, when we stick which we're going to do, with our thermochemistry lab, we stick a thermometer in something, we measure the temperature. How is that thermometer able to register the temperature? Which one of these three? Most likely. Induction, right? It's in contact with the medium and it transfers energy across that very thin glass wall into the bulb. And that causes the fluid inside to expand. We measure a temperature. Okay. We can, and I've said it before, I haven't said it in quite a while, is nature just does what it does. And it's going to do it whether we study it or not. And when we study nature and natural phenomenon, we try to make sense of it. And we categorize things. And one of the ways that we categorize energy is either as potential energy or kinetic energy. We can have potential, and potential energy just means that there is a potential by some means of extracting that energy from a process and transferring it to something else. The potential's there, we just don't realize it yet, but we can measure it. And one of the ways to measure it is by position. So potential energy can be attributed to position. And usually what we mean by position is where is that object in the gravitational field? In other words, a large heavenly body like the Earth, we're standing on the surface, we feel a pull to the center of the body. That's gravity. If I climb stairs and get on the roof, you know, I've added maybe, well, technically 1 story, but it's closer to 2 by the time you get up on the roof. I've added energy to my potential by expending energy and walking up the stairs or climbing the ladder to get on the roof. So now I have more potential energy due to my position, my relative position between standing on the ground and standing on the roof. I've added to my potential energy. Okay. Now it's not lost, it's just stored. It's available. All I have to do is jump off the roof and I'll get all that energy back. You know, it won't be fun, but I'll get it back. And by the time I hit the ground, just before I hit the ground, I've converted that potential energy into kinetic energy, movement. I'm moving faster as a consequence of the conversion of potential to the kinetic energy. We can also have potential energy based upon composition. And that's largely where chemists operate. Composition like chemical bonds, things that hold atoms together. There's a potential there. Some of them have a higher potential energy than others. For instance, nitroglycerin. Right? Stored in the bonds of nitroglycerin is massive amounts of energy. So all you have to do is just look at it cross-eyed and it'll blow up. Okay. Or Alfred Nobel found a way around that. He just combined nitroglycerin with kieselguhr, which is a mineral actually derived from diatoms, little bodies that they've dyed and stored in deposits. Stabilized it. But still, if you shock it big enough, it will give up that energy. That's energy of composition. That's chemical energy of composition stored in the bonds. You can also have electrostatic energy, repulsion or attraction. So if I have 2 charges that are big enough, and well, actually a better illustration would be the Van de Graaff generator. You ever seen one of those? It's like a long tube with a square base, and there's a big silver globe on top. And you plug it in the wall and you turn it on, and it transfers charge, electrons, to that silver ball. And shortly after it gets started, if you get close to it, you're grounded, you reach out to it, you see this big lightning bolt go from the thing to your finger, and it hurts. So we're storing energy in charge difference, and the energy is released when you get zapped, or when you walk across the carpet on a dry winter day and drag your feet, and then you grab the doorknob and bam. Or I've noticed sometimes when I grab a grocery cart at Sam's and walk around Sam's for a while, and it's got the plastic insulators on it, and my hand slides off to the side and gets close to that metal, I get popped because I'm building up electrostatic charge. That's stored energy by electrostatic composition. You can have, I can store energy in this rubber band, right? I have to expend energy to make it do that, right? But it's stored in the elastic polymers of this band. And to get it back, all I have to do is let it go. When we were kids, my brother and I used to take advantage of that. We'd take a piece of wood and tape a clothespin on one end of it, notch a hole in the other end, stretch a rubber band, and that would be we'd have gunfights. I was older than my brother and a little more mechanically inclined, so my rubber band gun had 3 clips around it, and his only had 1. So while he was reloading his, I could shoot him twice. But that's elastic composition. Magnetics work similarly to electrostatic attractions and differences of positive and negative charge, northern and southern charge. We have massive amounts of energy stored in the ionosphere around the Earth. Part of the reason that we have that energy stored there is because of the natural magnetic field that the Earth generates. We have part of the Earth's core is liquid, and it's circulating. And circulating ions create magnetic poles. So we have a North Pole, we have a South Pole, and the lines of magnetism go around the Earth like that and back into the Earth. And that gives us some protection against ions, the sun's plasma discharges. When they strike that, they sort of go around the Earth instead of stripping our atmosphere off, like they think happened to Mars. Mars has no atmosphere because it doesn't have a magnetic field. So we have stored energy in our magnetic field. Mars has none. So that's one major barrier to terraforming Mars. Theoretically, you could replenish its atmosphere, but as soon as you do that, the sun's going to strip it away anyhow. Nuclear stored energy in nuclear phenomenon, like you split the uranium-235 atom, and if you have enough of it together, you can get a big bomb. Or if you have it more diffuse, you can split those atoms and derive energy for peaceful purposes. And then of course, there's thermal energy. Which way does heat move? From high temperature to low temperature, right? So you can store a lot of energy in a high temperature device and extract that energy by causing it to transfer to a colder sink, and on the way, extract that energy. I read an article not too long ago about a type of heat battery that was composed primarily of just graphite. There's a big block of graphite, looked like one of these shipping crates. And they have built into it ways to add heat to it or extract heat from it. And it's more efficient as a store of electrical energy. They use electricity to heat it up. And then when they dump the heat out, they extract electricity from it. It has to be pretty hot. That's why they use graphite. But it's stored thermal energy. So we got potential energy due to composition and composition. Now, the difference here between potential energy and kinetic energy, kinetic always refers to motion. Something has to move in order to have kinetic energy. And we can actually, there's a formula for that. Kinetic energy is equal to mass times velocity squared. 1/2 of that value will give you the kinetic energy of any particle moving at a certain velocity. So there's a relationship between this and heat. Because heat is measured by its temperature and by its mass. But how does it get that heat? Well, the heat is actually motion of the molecules within the substance. Now, they can be, if it's a gas, they can move a certain distance before they smack into somebody else. But there's an average kinetic energy for all the molecules in a sample of gas. And we measure that kinetic energy with its temperature. So there's a link between kinetic energy and heat energy composition. There's your formula. So with that respect, kinetic energy is simpler to understand. It's just mass moving at a certain velocity. So electrons can have kinetic energy. Actually, the particle nature of light allows it to have kinetic energy also. You have bona fide ions streaming out from the sun, but you also have light. And there's one group of engineers, a diffuse group of engineers who are trying to build spacecraft that use solar sails. In other words, they deploy these big mylar screens that look they're miles across. And they catch radiation from the sun and it accelerates that space probe to pretty fantastic speeds just by catching light and particles from the sun. Okay. Now, let's talk about transfer of energy between potential and kinetic. In this figure, we have two balls, A and B. A is at a higher position, so it has more stored potential energy, whereas B is at rest and A is being held in place for now. So you can imagine that what we're going to do is let A loose and let it drop and see what happens. Okay. So A is going to move, and when it strikes B, B moves also, and A stays put. So A has given up its potential energy. Its kinetic energy has been acquired from its potential energy, and then it transfers that energy to B. And B now acquires some kinetic energy, and it moves up to that first ramp, that first level. Well, based upon where it was, it didn't get all that energy back, did it? Right? B should have gone up to that top level. I mean, if it were 100% efficient, B should have gone all the way up there, but it didn't. So if we're going to abide by the law of conservation of energy, where'd that energy go? We can't destroy it. It had to go somewhere. So where did it probably go? It went to heat, right? Friction, heat. We lost some of that energy to friction in the collision, in the movement of B across that surface. So with an accurate enough thermometer, we could measure the difference in temperature for the ramp and B, and A for that matter, and see if we're correct, account for all the energy. But that's Take my word for it. That's where it went. It's frictional heating. And you know, I mean, what do you do in cold weather, right? If you don't have gloves, right? Your hands get warm. That's friction. You've expended energy through your muscles and it went into heat. Okay. Let's see. Why am I pausing for clarification? Oh, the difference between temperature and heat. Unfortunately, popular media used to be just radio, television, and newspapers, magazines. Now, social media and the internet are adding to the confusion, right? There is a difference between temperature and heat. They are related, but they are different concepts. Temperature is an intensive property. That is, if I measure the temperature of a substance and it tells me it's 55 degrees Celsius, and I have that same substance, only now it's 10 times as big, 10 times the mass. The temperature will be the same, right? Now, there is more heat in, say, 10 kilograms than there is in 1 kilogram at the same temperature. But the temperature is the intensive property. It doesn't matter how much you have. That temperature is the same, regardless of the mass. But the amount of heat it contains is higher for the 10 gram. So heat is an extensive property. It's, well, let me get this point out of the way first. We know now that temperature is a measure for the average kinetic energy for all the molecules in a substance. If we say the temperature is 55 degrees C, that doesn't mean that every molecule in that substance is moving at the same velocity. It just means the average velocity of all those molecules indicates the temperature. They will usually have a distribution of bell-shaped. You ever heard of the bell-shaped curve? They usually have a bell-shaped curve. But the average kinetic energy is represented by the temperature. Heat, on the other hand, is a measure of, in fact, it's not just a measure of the heat content of that 10 kilogram mass. Heat can only be determined by transfer. In other words, if this substance is at a given temperature, and I know the mass of the substance, the only way to tell how much heat is there is to transfer to something else at a colder temperature. If this has a lesser temperature than that, then heat will transfer, and that change is a measure of heat. It's a transfer of energy. Now, we've developed ways to express the heat content of something, and we're going to do that. But that heat content was determined by transfer. Okay, I know I'm splitting hairs, but it's true. And like we said before, heat always moves from higher temperature to lower temperature. So when we use the Kelvin system for temperature, well, that's based upon absolute zero. In other words, nothing is colder than absolute 0 K. Well, 0 K is theoretical. Because how do you measure temperature when you can't transfer energy? If you're at 0 K, there's no place colder to transfer energy, right? So it's a theoretical value. Scientists have been able to come very close to, right? In bulk, we can get close to K with, I think liquid helium is the coldest bulk substance that we can produce. It's at 4K, just 4 degrees above absolute zero. But if you want to get any colder, you need a heat sink that's lower temperature. So that's why we'll never reach 0K in bulk. Now, there's some scientists that claim that they've reached absolute zero because there's no motion, there's no kinetic energy in the molecule. And they do it by positioning lasers so that an atom moving toward them, they hit it with a laser just enough energy to stop it. That's 0K technically. Okay. So, and what's the SI unit for energy? Remember what that is? It's the joule. Okay. And we'll come back to that. Okay, it's definition time. We mentioned earlier that energy is the ability to do work or to produce heat. Okay, so the work part of that can be expressed in these terms, and this is from physics. Work is force times distance, which means that if you apply a force to an object and it moves a certain distance, then work has been done. You have to do work to get it to do that. If I stand here and push on this wall, I'm expending energy, but I'm not doing any work because the wall's not moving. But I'm expending energy. Where'd that energy go? Heat, friction, right? So there are 2 ways to express energy in the scenario that's coming up. One is work and one is heat. Let's put so you got W equals work, and later on we're going to talk about heat, and we give that the symbol Q. Now, what do we mean by state versus path functions? State versus path. A state function is the description of a process in which the you only need to know the beginning and the end parameters. Energy is one of those. So when we express energy or a change in energy, we don't care how it got there, went from this point to that point. The difference in energy between those 2 points in the process is a path function, is a state function, excuse me, state function. But, illustration of that. If I change my elevation by starting in Charleston and ending up here in this area, I've increased my elevation by about 2,500 feet, roughly, like half a mile. Actually less than that, probably closer to 2,000 feet. Okay, so the difference in my potential energy only depends on the fact that I was at Charleston's elevation, now I'm at Beckley's elevation. But the amount of heat that was expended in the process of running my automobile's engine is a path function. In other words, it'll take a certain amount of heat to get from position A to position B. If I go straight, if I go from Charleston to Beckley straight, right? The difference in these two heights is a change in energy. But if I choose not to go by the turnpike, say I go the old route, you know, the back route along the river and then up through the woods and squirreling around, then those differences there will require more heat than this direction. So heat then is a path function. It requires knowledge of how you get from point A to point B. Okay. I understand these are strange concepts. And really the best way to get a handle on them is work problems. Solve problems using what we've learned here. Okay, that's a state function, path function. Okay, we covered those. Okay. Unfortunately, we need some more definitions. Because when we start talking about transfers of energy, we have to have a definition of what's here and what's there. And what we do is we define what a system is. And everything else is surroundings. Because if we're going to transfer energy of any kind from one place to another, there has to be a differentiation between the two. Otherwise, you know, you just make something up. Well, we do make something up, but we say this is the boundary. So we can transfer heat into the system from the surroundings, or we can transfer heat out of the system into the surroundings. Okay. And the system can be devised for convenience. What is the system? You define the system based upon what allows you to solve the problem. Right. So for instance, if we light the Bunsen burner in the lab, and what's the system? Well, the system is the part of that flame that in which the chemical reaction occurs. So the flame is the system. Now, everything else is the surroundings, and we know that that flame is producing heat, which is leaving the system. How do we know that? Because you get close enough, you can feel it, and you can see light coming from it. So we know that heat and energy of any kind is being transferred out of the system. We define the system as the flame. Now, if we leave it like this, what do the surroundings consist? The rest of the universe. That's kind of hard to get a handle on. So what we have to do for convenience again, and for the ability to solve real world problems, we also have to limit the surroundings. So now we're saying the surroundings are only this part of the universe. Oh, I got an animation for this one. Okay, system and surroundings. And then we limit the extent of the surroundings. Now, there are three ways to describe our system in terms of stuff moving across that boundary. Right? An open system is one in which both matter and energy can transfer. And a lot of systems in the natural world are open. But many of them that are open can be modified, especially living systems, like a leaf, right? During the day, a leaf will transpire, and the stomates will open and allow gas exchange, right? So the system being the leaf, freely energy or matter can move across that boundary. But at night, those stomates close up, and so that certain chemical reactions can occur without the influence of gases from the outside. Now the system is closed. It's closed because now matter cannot cross the boundary, but energy can still cross the boundary. That's the difference between open and closed. The third one limits both matter and energy, and it's called isolated. Okay? So this system can be isolated from its surroundings. Now, as a practical matter, since we don't want to have to account for all the energy or matter transfer into the entire universe or from, the limits to our surroundings must be isolated in order to be practical. When we do our thermochemistry experiments, when we come back from spring break, our system is going to be 2 styrofoam coffee cups. And that system now is isolated from its surroundings. So everything that happens in Vegas stays in Vegas. And we'll talk about that in more detail later. We might not get to that till Thursday. Right, because I've only got a half hour left. Okay. Now, when heat transfers into the system, and then when we describe what's happening across this boundary, everything is in reference to the system. So when heat goes into the system, it's endothermic, into. So this would be endothermic. And any calculations or measurements that put a number to that in terms of joules, the value would be positive because heat is being added to the system. So the other way around, this Q would be negative, and it would be called exothermic. It's leaving the system. And that's a convention we use for this and for many other things. Wherever we have a system surrounding definition, then the values would be positive into and negative out of. All right. So let's see if we understand this concept of system versus surroundings can be tricky if you don't think about what is the system in terms of its in opposition to its surroundings. So is the freezing of water an endothermic or an exothermic process? Well, what's the system? It's your water, right? Water. So water's here. If it's going to freeze, it's got to get colder, correct? So it has to be an exothermic process to freeze. Okay. All right. So here's some others. In this case, we're going to allow the questioner to define the system. So in this case, your hand gets cold when you touch ice. If your hand gets cold, heat transfers out of your hand, correct? That's an exothermic process. Ice gets warmer when you touch it. If ice is a system, then it's endothermic. Water boils in a kettle. Okay, water's the system. If it's going to boil, it has to get hotter. It's endothermic. Water vapor condenses on a cold pipe. If the water condenses, it has to lose energy for the phase change from gas to liquid. So that's exothermic. It has to lose energy from that system, from the water vapor. And ice cream melts, that's endothermic. The energy has to transfer into the ice cream in order for it to melt. Okay. For each of the following, define a system and its surroundings. So in this case, we get to define what the system is. And we try to be logical about this. What makes the most sense? what allows us to solve the problem most efficiently, and then give the direction of the energy transfer. For a chemical reaction, the balanced equation is the best means of defining the system. That's true. Like our Bunsen burner. It's natural gas is primarily methane, and we're going to add oxygen to it, and it's going to produce carbon dioxide and water. Right? And at those temperatures, water is going to be a gas. So everything's gas. Let's see. That's not balanced. Let's see, there's 1 carbon, 4 hydrogens. Now we got 2 and 2, so that's 2 here. There we go. That's balanced. So our system is the chemical reaction. That whole reactants and products is our system. So methane is burning in a Bunsen burner. That would be exothermic. It's giving up heat. And where was that heat before the reaction? It was contained in the chemical bonds. So when we have to break bonds between carbon and hydrogen, break bonds between the oxygen atoms. So we have to put energy in. But when we reform the bonds, they are at lower energy. The higher energy here, let's see, we put energy in here, then at a lower energy, they give up more of that energy that was there. So that makes it exothermic. Water drops sitting on your skin have, after swimming, evaporate. Well, what do we want to call the system? Maybe the water drops? If we're saying the water drops evaporate, then it makes sense to say the water drops are the system. That's endothermic. Okay, hydrogen gas, oxygen gas react violently to form water. All right. It's kind of hard to use the space shuttle analogy anymore because we don't fly those anymore. But the main engines of the space shuttle were fueled by hydrogen and oxygen from that big orange tank sat on the outside. You could run it through the engine, and gain velocity and get into orbit. Or you can burn a hole through the side of the tank with one of your solid rocket boosters and blow it up and halfway to your destination and kill everybody on board. The reaction is still the same. The chemical reaction is the same no matter how you do it. So if hydrogen gas reacts with oxygen gas to produce water, okay, and let's see, we need 2 of those and 2 of these, then which is lower in energy? If this is exothermic, if heat is leaving the system, so that means it'd be negative. If heat's leaving the system in this process, then what is the budget of the energy? Well, the easiest way to look at a chemical reaction like that is if it's exothermic, energy would be a term on the product side. So that's why I like to do that. Put my Q over there for, that's supposed to be a Q. Looks more like a G than put the energy where it is descriptive of the reaction. So an exothermic would be here. Okay, what does that say about the total energy? Well, the total energy here has to be the total energy there, right? So if part of the energy is here, that means the energy of this product has to be lower than the energy of the reactants. Okay. So water has a lower total energy as compared to the reactants. Okay. Now, thermodynamics is an umbrella discipline that includes thermochemistry. And we've talked about the first law of thermodynamics, that you can't create energy, you can't destroy energy, you can only change it. That's delta E equals 0 for the entire universe. Now, on a local scale, right, if we draw this, then the delta E in here can be a positive or a negative value, because we've isolated from the rest of the universe. That value, that expression only works for the entire universe. More definitions. What is internal energy? And we still use this as internal energy. So internal energy of a system is the sum of all kinetic and potential energy of everything in the system. That's total. We have to account for everything in the system. So the internal energy is what energy is in that system. Well, it's not practical. I mean, we've defined the term, we've defined the symbol E as internal energy, but the only way to know that there's any internal energy there is to measure a transfer. So we typically write it this way: delta E. What's the transfer of energy? Well, the transfer of energy can come in two forms. The transfer of energy now we would have to measure between system and surroundings in order to know it's even there. So we've identified the Q values, but we can also say the same thing for work. So if work is being done on the system, that's a positive value. If work is being done by the system on its surroundings, that's a negative value, because everything is referenced to the system. One way of measuring work is this force times distance. And we're going to use that relationship to investigate how that a way of expressing it based upon gases. Okay. Thermodynamic. Okay. I thought I was going straight to that right now, so I guess we'll hold that thought. We express thermodynamic quantities in three parts. Oh, yes. The number gives the magnitude. Then you have units of measure, of course, but you also have a sign that's extremely important, because that tells you whether it's going into or out of the system. Okay. I'm not going to spend much time on these slides because I've already told you what that means. Q's are positive for endothermic and negative. It's always in terms of the system. Oh, Professor Dave wants to talk. Let's see, we have time. Okay. That's only 4 minutes. Let me turn up the sound.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released, but it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, running out of time. He introduced some terms there that we haven't fully fleshed out yet. And I want to get through this discussion before I run out of time. So I mentioned force times distance is an expression of work. And we're going to do some math to associate that value for work, force times distance, to relate it to gas, a trapped gas. So here we have a cylinder of gas on the left of that figure, and the pressure on that gas is force per unit area. We've studied that before. If we allow the gas to expand a distance of delta H, small h, that would be the distance, then since the area is the same for both of them, then we have a relationship between the pressure and the force. Okay, so we've got a force bearing down on that gas, and now it's moved up. Well, first of all, that's a change in volume, not just a change in distance. We've changed the volume. And lost my train of thought. Oh, what's the system first? It's the trapped gas. Okay, so if the gas is expanding, who's doing work on what? The gas is doing work on its surroundings as it expands. It's pushing against some external force. So that value for work should be negative, right? This is doing work on its surroundings. So it should be this one right here. Okay, that's the first thing. The second is to substitute some expressions into the force times distance. Okay, so we have pressure equals force times area. Force then is pressure times unit area. So now we have a relationship that we can substitute pressure times area into the F term. And we also have a change in volume, which is distance times, diameter. Let's see, is that right? No, distance times area is volume. We should have used H in there. It's kind of confusing. So D and H are the same. Change in height. If we solve for the distance or the H, then we get a change in volume divided by area. Now we can substitute for F and we can substitute for distance. And we come up with this expression. P times A for force, delta V times A for distance. And the A's cancel because one's in the numerator, one's in the denominator. And our work then is an expression in terms of pressure times change in volume for a gas. Okay, so now we have another way of saying work. Pressure times change in volume. Okay. Now there's a problem here. The change in volume is a positive value. Change in pressure is constant. So that means W, if we calculate it that way, this change would be positive because it's final minus initial. So final volume is greater than initial. That's a positive value. That gives us a positive value here, but we just said that it should be negative. Okay. So by convention, and to make sure that all the equations come out right, we stick a negative there. So for calculation purposes, work in a gas is equal to minus pressure times change in volume. Okay. These conversion factors are in useful information. That means that it'll be available on the exam. Just learn how to use them. So what would we get here if we used conventional values? Pressure would be, say, in atmospheres. Change in volume would be in liters. So that's liter atmospheres would be the units of measure for this value. But liter atmospheres is not joules. We need a relationship between liter atmospheres and joules. And there it is. 1 liter atmosphere by this calculation is equal to 101.3 joules. So which of the following here performs more work? If we're under a 2 atmosphere pressure and we go from 1 liter to 4 liters, what's that difference? What's the change in volume? 3, right? 3 liters. It goes from 1 to, so that's positive 3 liters. And then the pressure is 1 atmosphere. So the work would be negative 3 liter atmospheres for that first one. Oops. Oh, I'm sorry. You didn't correct me. 2 atmospheres. 6 liter atmospheres. Okay, what if we expand a gas under a pressure of 3 atmospheres, only now it goes from 1 to 3, so it's only 2. So 2 times 3 is 6. It's exactly the same. 6 liter atmospheres of work were done in either situation. Same amount of work is performed by the system on its surroundings. Okay, I'm gonna have to erase this to make room for the rest. And I've only got 5 minutes to do it. Let me see what's coming up. If this is a more convenient place to stop. I got a break point in here, but I took up too much time. Okay. Yeah, let's do this slide and then we'll pick it up on Thursday, which would be just 3, 6. Okay, let's finish this one. So determine the sign of delta E for each of the following with the listed conditions. And that now we're referencing this equation here, delta E equals W plus Q. The total change in internal energy for our system can be calculated by adding the work that the system does on its surroundings or is done on the system, plus the heat that it gives up to the system or absorbs from the surroundings. Okay. So if we have, we want to know the sign on delta E for these situations. For the first one, we have an endothermic process. So an endothermic process means heat into. So that's a positive value. That performs work. So in that case, in the first case, if work is greater than the heat term for an endothermic process, this is positive, and the process performs work that is on its surroundings. So the work now is negative. Work is being done by the system. Okay. If this is greater than Q, then delta E must also be negative. Okay. The other way around, if work is less than Q, then this value would be positive. Okay. Now, if work is done on the gas and the process is exothermic. So if the process is exothermic, right? And again, we have work greater than Q or work less than Q, but this is now negative. And work is done on a gas, so it's positive. Okay, for both situations. If this is greater than Q, change in internal energy is positive, and the other one would be negative. Okay. So for this situation, the internal energy of the system is decreasing. For this one, it's increasing. For this one, it's increasing. For this one, it's decreasing. The total energy in the system is changing that way. See if I did it right. Okay. All right, so next thing we're going to pick up with change in enthalpy. We're going to define what enthalpy is. I think this is a good place to break. We left off comparing, well, let's just back up and see. There. We left off with a comparison of using this expression where change in energy of the system can be quantified as movement of heat or work. So we ran through those different scenarios for endothermic and exothermic processes. And now we just want to hammer home this point that when we talk about the Q of any process, it's an actual measured quantity. So we would have our system, and then we would have our isolated surroundings. And measured heat moving into the system, of course, is going to be a positive value. Measured heat moving out of the system is going to be a negative value. But often you'll hear this term enthalpy. Enthalpy, which is given a delta H value. Enthalpy is similar to heat in terms, in fact, it's a measurement, not a measurement per se, but it's an expression of heat for a reaction, but it's more the heat potential that can either be derived from the reaction or have to be added to the reaction mechanism. So they're related, they're like cousins, but they're not exactly the same terms. And there's the definition of Q, the actual amount of heat that moves into or out of a system. And then, of course, we just threw in this extra term, work. That's the other way we measure energy, change in internal energy. Remember, this is internal energy. Internal energy for a system. And it can be quantified by either by a summation of heat movement and work done. Okay, enthalpy is the best way to think of enthalpy as a potential. And if we remember, we had the possibility for either a state function or a path function. And the state function simply requires only that you know the state of the system or the transition from this place to that place. It doesn't matter what happens in between. Well, state functions, delta E is a state function. Delta H is also a state function. So it only matters the beginning and the end. What happens in between doesn't matter. Whereas a path function would be Q or W, either one of those. It does matter, the measurement of either Q or W does matter the path that's taken. Okay. Now we can, we don't have the time and I don't have the expertise to explain how we came up with this formula, but the change in enthalpy is related to the change in internal energy plus any changes in pressure times volume. So if it's not a gas, then this doesn't matter. If it's a gas, then that matters. So what we're aiming at here is to say this is a valuable piece of information that you can know about an equation, but this is the only one that can be measured. Okay, so what we want is and I'm going to show you mathematically how you can relate these two so that we can measure something and then relate it to a value for enthalpy, the potential for the system. Okay, so we have, by inserting the equivalence of delta E, we just plug in delta E for these two values. We have Q plus W plus delta pressure times volume. Right. So that's all we've done. We've just done a substitution there. If the process takes place at constant pressure, So under what circumstances would we want constant pressure? Remember, for gases, we had pressure, volume, temperature, and moles. So if we have constant pressure, then we could have either constant moles, which is more likely, and then volume and temperature would be allowed to change for Charles' law. So under conditions of constant pressure or volume moles for Avogadro's law. But if we hold pressure constant, then this pressure term comes out, and now it becomes pressure times change in volume, because pressure now is constant. Okay. So this is the state of our equation up to this point. And that should be on the slide also. There we go. Okay. So we also know that when we derive the formula for work on or by a gas, an expanding or contracting gas, and we determined that that was W equals minus P delta V. Okay, remember that from last time. Okay. So if we substitute that for W, then we have to stretch it over here. This delta H equals Q plus, and then that term, which is minus P delta V plus P delta V. Notice that with this expression now, this is a plus and this is a minus, they cancel each other out. So what we're saying is, under these circumstances, the measured value of Q, the heat transfer, is equal to enthalpy if pressure is constant. So that's why chemists tend to conduct experiments whenever possible where they can hold the pressure constant for the reaction. Then any heat transfers they measure is directly convertible into enthalpy. All right. Okay, so let's say let's see, I want to be sure I didn't miss anybody. It looks like I got it, buddy. Yep. So let's say you are studying, I better make some room up here. Back in the old days when we didn't have slideshow to go along with it, I had more boardroom. Let's say you're studying a process that takes your system from one set of pressure, volume, temperature values to a pressure volume, a different set of pressure, temperature values, 1 and 2. There are a number of different paths that we can take between these two thermodynamic states. We could go, we could start with, say, volume 1, and then we could increase the volume to, say, volume 1 prime, and then we could come back down here to volume 1 double prime, and then we could come back up maybe to here to volume 2. So we've gone through a circuitous route to get to the last volume. That's just one possible pathway. We could have gone down here and back up here and down here and back up there. Eventually we end up in the same place. But we've taken two different pathways or multiple pathways to get there. Along each of these pathways, we would measure both Q and W as we go. So if we take a route that goes down here, here, like this, like that, and then back down here, then you can see that the Q and the W's as measured would be different for each one of these pathways. But since this is our starting point, this is our ending point, the difference between the two, here to here, is a delta V that that also means any changes in heat or work heat in particular, enthalpy, that we experience between these two places, doesn't matter the path. So the good thing about that is if you know the a standard value for the enthalpy of products or a reaction. And I'll show you how that works in a minute. And subtract the enthalpy of the reactants before the reaction occurred, then that's equal to the overall enthalpy for the reaction. So it doesn't matter the path, we can calculate if we know the enthalpy for the products, the enthalpy for the reactants, we can calculate the enthalpy for the reaction. And that's useful, especially for reactions that we suspect might be hazardous, might be extremely exothermic. Then we can calculate what to expect from that reaction and modify our conditions to be safe. Now, with these conditions where we went from P1 to P2, if P1 and P2 are different, then we cannot equate enthalpy with Q. But if P is constant throughout all these processes, then the total amount of heat transferred is the same as the enthalpy. Okay. That's just a reminder. All right, so here's a sample equation with the listed enthalpy. So we've got propane, right? And we're going to combust it with oxygen. And that, if the combustion is complete, it always leads to carbon dioxide and water. Let's see, three, we're going to balance the equations here. Now, you can tell from the enthalpy value, delta H equals a negative 2.221 kilojoules per mole. That is a huge number. So you understand why propane is used to heat homes, cook your food, barbecue your steaks, you know. I will make one comment. With all that heat, you would expect the water to be gas state, right? But this whole equation is quantified in terms of standard state. So, and standard temperature and pressure. So standard temperature and pressure for chemical reactions. Now, when we were studying gases, standard temperature was 0 degrees Celsius. But for all other reactions, standard temperature is 25 degrees Celsius. It's still 1 atmosphere pressure. So under these conditions, right, we allow the heat to be send it to a heat sink and maintain standard temperature for the whole process. Then this is what we get coming out of it with water as a liquid. Okay, so if we allowed water to be a gas, this value would be different. It wouldn't, if it were a gas, this probably would not be as large because some of that heat would still be contained in the gaseous water. But when we condense it, that gives up more heat and that makes this bigger. Okay, that's a technicality, but it's true. Okay, back to the problem. We want to calculate the delta H in which 5 grams of propane is burned into excess oxygen. So oxygen's excess, and this is 5 grams. And we want to know what's the enthalpy for that reaction? Well, sometimes the enthalpy is reported in terms of joules or kilojoules per mole. But sometimes that part is left off. And that's not a problem, because if this is reported for that reaction, this is 2,000 kilojoules for 1 mole of propane, or 2,000 kilojoules for 5 moles of oxygen in this reaction, or for 3 moles of carbon dioxide or 4 moles of water. So you can set it up with this value depending on what's needed. It can be this many kilojoules per 1 mole of that, or per 5 moles of that. Any one of them will work depending on what you need. So since we're actually working with propane, this will be that many kilojoules per mole of propane. So what we need is to figure the moles of propane. So we would do 5 grams of propane and convert those units to moles. Right, there we have a quotient with grams and moles. That means we need molar mass. So carbon is 12.01 for each one. 3 times 12.01, and 8 times 1.01 for the hydrogens. We just add those together. And 8.08. So that's 44.11. And we divide that into 5. And I get 0.1134 moles of propane. Now we can calculate, based upon the enthalpy of the reaction, minus 2,221 kilojoules per 1 mole of propane. And that will cancel out, and that should give us the answer we're looking for. Let's see, 2,221, change the sign, and times. So I get minus 251 C. Actually, this is, oh, I get 3 significant figures. Okay. Minus 252 kilojoules. Okay. If I did it right, should come up with, yep, minus 252. So that tells us how much heat will be evolved when we combust 5 grams of propane. Let's see. Do I need to keep that up there? No. Okay, we're going to talk about calorimetry next. And this is going to be a useful topic, because that's what we're going to do the first lab we come back from spring break, is calorimetry. And this is the way that we measure actual heat transfer in a reaction. Is this process, calorimetry, science of measuring heat. Calor, of course, refers to heat, and metry refers for meter, to measure. So we're measuring heat. So how do we measure heat? Temperature change. That's the only way we've got. We measure the temperature change, and then other factors we feed in there, like the mass relationships or mole relationships go into the calculation. But the temperature is central. Now, definitions. Before we get to specific heat capacity, let's say heat capacity. Heat capacity equals the number of, well, we're going to use joules. When I was a student, we used calories. But in the interim, in the intervening 50 odd years, we've moved over to joules instead. So it's heat capacity is the number of joules absorbed or evolved for a given mass. So this would be an extensive property. That means, and actually, joules absorbed or evolved for a given mass per degrees Celsius. So for every degree change in Celsius for this mass, there's a certain amount of heat, joules, absorbed or given up. That's an extensive property because if we have more mass, we have a higher capacity. Okay. That's not very useful. Well, it is useful for us because this is the expression we're going to use for the calorimeter itself. Because the calorimeter in which we conduct our experiment is a heat sink. And it will absorb heat from the reaction if it's produced or provide heat if the reaction absorbs heat. Okay, so this is something, and it's usually given a big C. Specific heat capacity, and I think your authors use a small s. Specific heat capacity takes this value and goes one step further and ratios it to the mass of the substance. So specific heat capacity is actually the units of measure then would be something like kilojoules absorbed per gram of the material per degree C. So for every 1 degree C, for a gram of that material, it will either absorb or evolve so many kilojoules. So those are the units of measure. And the only thing we've added here is the mass of the substance. So we've ratioed it to the mass. That makes this an intensive property. So it doesn't matter how much you have, what mass you have, this value will be constant for that. Like iron will have a certain specific heat capacity. Air will have a certain specific heat capacity. Now, the modification to this is, and I'm not sure what symbol they use, S sub M or N would be the molar specific heat capacity or the molar heat capacity. And its units of measure would be something like kilojoules, or it could be joules per mole degree C. Okay. And sometimes it'll be reported as kilojoules per gram K or kilojoules per mole K. And they're exactly the same number because the unit of measure for degree C and K are exactly the same. So it doesn't matter really which is which. But this is based upon mass and this is based upon moles. So sometimes this is actually more useful, particularly when you're talking about chemical reactions. Okay. Let's see. I'm gonna have to make room, sorry. If two reactants in solution at the same temperature are mixed and the resulting solution gets warmer, this means the reaction taking place is exothermic. Temperature increases in our reaction vessel, then the reaction itself is exothermic. Good example of that is, have you ever taken it's not as likely to find it anymore, but I think you can still get them. Solid Drano, which is pure sodium hydroxide. And we used to just take the solid and pour it down our drain and then add water to it, and it would clean out the hairs. It would hydrolyze proteins and clean the hairs out of our gutter, out of our trap. Well, if you measure the temperature, let's say you put that into standing water and let it dissolve, you measure the temperature before and after, you're going to find the temperature goes way up. I mean, it gets hot. If you try to do that in a plastic vessel like Tupperware, it'll melt. It's that hot. And this is typical of concentrated acids and concentrated bases going into solution. They're extremely exothermic. That's why the rule of thumb is do as you ought to, add acid to water. Because if you add water to acid, then the amount of heat generated is enough to vaporize that water on an instant, and it will spatter. So you add the acid to a lot of water, and that has a higher heat capacity because it's more mass, and it will moderate the temperature increase. But that would be an exothermic process. An endothermic reaction gets colder for a solution, and those the hospital bags where you break the capsule inside the bag and shake it up and get cold, that's an endothermic process. It's like, well, it got heat bags too. It's a different salt in that capsule for each one. One of them, typically as it goes into solution, absorbs heat. The other one generates heat. We talk about that second semester. More detail. Okay, Professor Dave wants to talk, so let's give him the floor.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchange in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, And this time, the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
That's enough of that. So we'll come back to these equations in a minute. This coffee cup, and for our experiment that we're going to do after the break, we're set up like this with a double cup. They're two styrofoam cups together. So we're aiming for an isolated surroundings. And with the system inside the surroundings. By isolating the isolated surroundings also isolates the system from the rest of the universe. So everything that happens in here must add up to zero. We can't create energy, we can't destroy energy. So everything that happens in here must be equal to zero. So the Q that is lost, say, if we're going this direction, that's lost by the surroundings, plus the Q that's absorbed by the system must be equal to zero. And that's very useful. In fact, the way that Professor Dave described this calorimetry experiment was the way they taught me as a student. And it was always difficult because you have to keep track of so many different factors that you say, okay, what's equal to what? But with this system, all you have to do is identify the Q terms in your isolated surroundings, and they're always equal to zero. So you can put as many Q terms in there as you need, as long as you know that adding them up equals to zero. It's kind of like a quadratic equation, like zero equals a x squared plus b x plus c. Right? It's always equal to zero. Or if you prefer, what happens in Vegas stays in Vegas. Okay, so this is what a coffee cup calorimeter looks like. Now they sell calorimeters, and I think I've got a few in there. They're just aluminum container with an inner aluminum container that's suspended in it. So you have that airspace that provides insulation. But, and I've used them before, but this works just as well. The one thing that we're not using now that I used to use in my coffee cup calorimeters was the stirrer. The problem with the stirrer is if you don't make it out of the right material, then it could corrode in your chemical reaction. And that's what happens to some of my stirrers. So I just eliminate the stirrer. And if you're careful with your thermometer, these student thermometers are pretty rugged. You can stir things with a thermometer. So we only have, and that also removes another heat sink from the calorimeter, because those stirrers are usually made of metal and they will absorb some heat or give up some heat. We can get rid of those. And just simplify the calorimeter to a double coffee cup with a lid and a thermometer. And that's it. So whatever happens in here, it has to be uniformly distributed and mixed. Okay, so we can measure the temperature before the reaction occurs and measure the temperature after the reaction occurs. And that fits into this change in temperature. You know, final minus initial would be this value. The final measured temperature minus the initial measured temperature. Now in calorimetry, the order that these are measured and calculated is very important because it changes the sign. If the final temperature is higher than the initial temperature, this is going to be a positive value. And if the initial temperature is higher than the final temperature, then it's going to be a negative value. Did I say that right? Final minus initial. Yeah, that's right. Okay. And we'll look at some examples. So this is an isolated, actually it's more than just an isolated system, it's an isolated surroundings. Well, you could look at it as an isolated system, right? If this were your coffee cup, then any heat transfers inside that system add up to 0. So either way works. But some way or another, it needs to be isolated. All right. So if we know what the substance is, like any pure substance, like an element or a compound, then it will have a specific heat capacity associated with it. And that goes into the formula. Or it could be an unknown that we're calculating. Then you have the mass of the substance and you have the measured change in temperature. And it's usually in terms of gram degree C or degree C grams in the denominator, joules in the numerator. It could be simply joules or it could be kilojoules. But I think more often than not, it's joules. Okay. So what we do is we set up our equation to consider all possible heat transfers out to however many you need. And the sum must always be equal to 0. Okay, let's try a concept check here. If you have a 100-gram sample of water at 90 degrees, that's 100 grams. 100 grams of water at 90 degrees C. And then you add to that, maybe I better make it less because I'll put some in there. And then you add to that 100 grams of water at 10 degrees C. And let them mix. What would you expect the final temperature to be? They're equal masses. They should have equal specific heat capacities. The only difference is the temperature. So in this case, when we add those together, we should expect to split the difference between 90 and 100, exactly in the middle, which would be what? Well, let's see, the difference between the two is 80 and half of 80 is 40. And we're coming up from 10 or down from 90, it doesn't matter. 40 plus 10 is 50 degrees. So that's what we expect the temperature to be once it's mixed. Okay. That was a simple concept. Now we're going to complicate it. Okay, so let's change the conditions. now. And we're gonna start off with 100 grams at 90 degrees. Okay, so we've got the same amount here. And then how much, and then we're gonna add 500 grams at 10 degrees. So we need a bigger cup. And now we have 500 grams at 10 degrees. Where would we expect the temperature to end up? Not exactly 50, correct? And it's not going to be greater than 90 degrees because there's more 10-degree water than there is 90 degrees. So it should be less than half, should be less than 50, between 10 and 50, I would expect. Okay, this is a semi-quantitative or a qualitative thought process. Now, what would be the final temperature of the water? Okay. So we're going to take this example, and we've got two terms in here. Added together should be equal to 0. So let's say the Q of the hot, the heat transfer from the hot, and the heat transfer from the cold. Those are our only two terms, and we're going to ignore the calorimeter for now. Just say the calorimeter has no contribution either way. So what we would do now is do the calculation for Q. So this Q would be the specific heat capacity for water times the mass of the water, and the hot would be 100 grams. And the difference in temperature would be the final temperature minus the initial temperature for this slug of water. So it'd be the final temperature minus 90. Okay, let's see, specific heat capacity of water is what, 4? Are they going to show us? Yeah, 4.184. Let's just go ahead and put that in there. 4.184 joules per gram degree C. Okay. So this is our first term. Sometimes I put square brackets around each term just to keep them separated. For the second one, we do a similar calculation with 4.184. I'm going to leave the units off there. This one is 500 grams. Its final temperature will be exactly the same as the final temperature for the 100 gram slug because now they're mixed. So the final temperature is going to be the same, but the initial temperature was 10 degrees. Okay, so there we have our equation in one unknown. And all we have to do is slug through it. This is the thinking part, the rest is number crunching. Right? So in the interest of time, it's there, the problem's set up. Okay, we get 4.184 times 100 is 400 and something times T sub F. And then times minus 90. So you get those two terms, the 418 times T sub F, and then 418 times 90 with a minus sign. So that's where those two terms came in the first part of the equation. We do the same thing on this one, and we get the other set of numbers, 2,000 and 20,920. Then we keep shrinking it down until we get the unknown on one side of the equation, which is now on the right-hand side is our unknown. So now all we have to do is divide 58,000 by 2,500, and that gives us 23 degrees. So our final temperature will be 23, and it's in the region we thought it would be, between 10 and 90, 10 and 50. 23 degrees is the actual temperature. Okay, so let's complicate it a little more. Instead of using water for both parts of the thing, we're going to have 50 grams of, let's erase these. So now we have, let's say we have 50 grams of water at what temperature? 10 degrees. Okay. Then we're going to drop a chunk of iron, correct? Iron ball, 50 grams. That iron ball at 90 degrees. Okay. So we want to know the final temperature. And we set it up the same way as before. Oh, estimate the temperature. All right. This one starts off at 90. This one's at 10. So it's going to rise. The temperature is going to rise here from 10 and drop here from 90. Are we likely to end up in the middle? Well, if you know anything about matter, water has a much higher heat capacity than iron. So it can absorb a lot of heat. So it's not going to move much from 10, but 90 is going to drop a lot. So it's going to be probably between 10 and 50. Now calculate the actual temperature. Okay, so we set it up the same way as before. 0 equals the heat change for water plus the heat change for the iron ball. Right. And again, we leave out the calorimeter. And this is what it would look like to set it up. We have a different heat capacity for specific heat capacity for iron than we do for water. It's about a tenth, not quite, almost a tenth of water. So it's much lower heat capacity. By the way, think about that in practical terms. What does heat capacity, a lower heat capacity, mean? That means the same amount of heat added to water or iron, one or the other. Which one's going to change the most temperature? Iron, because it has a lower heat capacity. In other words, same amount of heat for iron will cause its temperature to increase by almost a factor of 10. So when you're looking for something that doesn't change its temperature very much for an amount of heat, you want a high heat capacity. And that's why water is, it makes this planet such a pleasant place to live. Because there's so much water on it, it moderates the temperature. I mean, if we were on a planet like Mars, right, with no water on the surface, right, any solar radiation coming in is going to change the temperature like that. It's even worse on the moon. Right? The difference between the dark side and the bright side of the moon, you cross that dividing line, your temperature is going to change by probably at least 500 degrees Celsius. Because vacuum has no heat capacity. Okay, so we've set up our problem with different heat capacities for water and iron. Even though they have the same mass, they have different temperature changes. And we can solve for the final temperature just like we did before. And we end up with 18 degrees. So the water didn't change as much this time from its 10 degrees to 23 degrees. Now it only went from 10 degrees to 18 degrees because water has a much higher heat capacity than iron. And at the end of the experiment, the temperature of both of them is 18 degrees. Okay. So iron went down from 90 to 18 and water went up from 10 to 18. Only an 8-degree change. Here it's a 72-degree change. Okay, this is where I normally would have paused if we had made it this far. So we're going to keep rolling. And I'll probably run out of time, so if you have to go at 1:45, go ahead and I'll finish the lecture and post the video. Okay, Hess's law. Obviously, Hess was a chemist who proposed this thermodynamic property of the chemical equations, is that if you're investigating an unknown equation and you're pretty sure the outcome of the equation, right? Products, the reactants and products, but you don't know what the heat generated by that reaction is going to be. Hess's law allows you to, since enthalpy is a state function, you can parse that equation into several other equations, which must add up to your target equation. And if you know the enthalpy for each of those component equations, you can calculate the expected enthalpy for the target equation. Probably make more sense if we actually do one or two of them. So it's not necessary to conduct the calorimetry in the laboratory, especially if it's going to be a hazardous one. And there's the safety part, part 2. Oh, okay, we're going to get, Professor Dave wants to talk again.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are 2 ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. Before we get the heats of formation, let's look at Hess's law. This reaction can be carried out in two distinct steps with enthalpy changes of delta H2 and delta H3. So these two equations have known enthalpies, where the nitrogen plus oxygen yields nitrogen monoxide, and nitrogen monoxide plus oxygen yields nitrogen dioxide. Now, we're given a value up there of 68 kilojoules for the overall reaction, but if we arrange these equations correctly, and it has been done for us already, and then cancel the terms that are common on either side of the arrows, then we're left with nitrogen, diatomic nitrogen, and 2 moles of oxygen yields 2 moles of NO2. So that's the first requirement for Hess's law to work, is the component equations must add up to the target equation. And in order to do that, we may have to flip equations, we may have to multiply times some constant. But when you do that and you get the final equation added up correctly, then you add up the enthalpies for the component equations, and lo and behold, the value is the same as that measured for the target equation. Now, this is a one way to look at what's happening in there. With a two-step reaction, you have to add energy in to get up to a certain point, but then you get energy back down to the level where you've produced nitrogen dioxide. Whereas if you use the single equation, you just go from 0 up to a certain point, and they're exactly the same for the one step. Okay. So this is just a rehash of what Professor Dave was talking about. If you have to reverse a reaction, you change the sign of the delta H. If you have to multiply an equation by some constant value, you also multiply the delta H by that constant value. Okay. So if we're given these reactions and their associated enthalpies, use those to calculate the enthalpy for the bottom equation. So the component equations are on the top of this slide and the target equations on the bottom. So sometimes it's useful in chemistry to work backwards. If you know what the end result needs to be, and all you have to figure out is how to get there, then start with the end result and work backwards. What do I need to put together to make the calculation give me the final result that's proposed in the problem. Okay. So here we have the same data again. And now what we're going to do is multiply the reactions to give the correct number of reactants and products. So notice that nitrogen is on the correct side of the equation for the component, the first one, as the bottom one doesn't have enough of it. So what factor could we multiply the top equation by to get 2 nitrogens? We'd have to multiply by 4. 4 times a half gives you 2. So that's the first thing we do. The second one puts water on the correct side, only we need 6 waters instead of 2, so we multiply that one by 3. And we multiply the enthalpies by that factor also. So now we have those corrected, and we cancel terms that are common on both sides of the arrows. And then we add things together, and you can see that 2 nitrogens plus 6 waters on the left yields 3 oxygens and 4 ammonias on the right. So now all we have to do is add up the enthalpies, and we get 1,268 kilojoules for that target reaction. Now for the standard enthalpies of formation. These values can be acquired from reference manuals, but they have to be written in the correct form. When we say the standard enthalpy of formation, we start with the product that's going to be formed. An example I'll use is ammonia. The standard enthalpy of formation for ammonia in what form? Under standard conditions, it's a gas. Okay, so we take each one of the elements. What's the most stable form of nitrogen under those conditions? It's dinitrogen as a gas. Okay. The most stable hydrogen is the diatomic hydrogen as a gas. Okay, so we form the compound from its elements. Now, the requirements are that the formation, the formed compound is 1 mole always. So there's an understood 1 here for any compound that we choose to use the standard enthalpy of formation. So that means these are going to have to be fractional coefficients. All right, so here's where we deviate from first semester learning to the simplest whole number for a reaction. We have to use fractions for this. Right? So how do you get 3 out of 2? 3 halves will give you 3 hydrogens. And here we need 1 half to give you 1 nitrogen. That would be the equation for the standard enthalpy of formation, and then we get a value. And that's what you would look up in your reference manual. Actually, when you go to a reference manual, standard enthalpy of formation, you just look up product, right? And some of them give you the equation that goes with it, some of them don't. They figure you're supposed to know. Okay, standard states, right? We said 1 atmosphere, yes, and 25 degrees Celsius. But also, if there's a solution involved, the concentrations are always 1 molar. Or if there are pure substances involved, they'll either be liquid or solid. And these gases would have to be at 1 atmosphere pressure, exactly, to generate the value of enthalpy that's reported in the manual. Okay, I don't think there's much to be gained from this, except to illustrate that when you calculate the enthalpy for a reaction, you're going to take the sum of the enthalpies for the products. Or the summation of all of these times actually we should put, you have to include the moles. So the value here, the delta H for this reaction is referencing 1 mole of that compound. If there's more than 1 mole, you have to incorporate that factor. So we sum up all the products and then we subtract the sum of the delta H's up to however many for the reactants. Okay. Now there's one other fact that we have to consider. The standard enthalpies of formation by convention for elements under standard conditions are always 0. The only values for enthalpies of formation are those which are formed from elements, compounds. So if you have an equation, a reaction in which elements are present, those factors are 0, but you don't even include them. Okay, so there it is in black and white. And the standard states formation for an element is always 0. Okay, so here for this reaction where we react sodium with water, and that's an extremely exothermic reaction. Right? Not as violent as potassium, but it's pretty good. Produces sodium hydroxide and hydrogen gas. So if you put some sodium in water, and it may get hot enough that once that hydrogen bubbles out of the solution and meets oxygen and air, could be enough heat to ignite it. Could have a flame on the top of your water. Those are 2 different reactions. So in order to calculate this, all we need to know is the standard heat of formation for sodium hydroxide and for water, because hydrogen doesn't enter in, sodium doesn't enter in. They're zeros. So if we multiply each one of those by 2, because sodium hydroxide is coefficient of 2, water's coefficient of 2, and put them into this formula, we should get a value of minus 368 kilojoules for that reaction. And the measurements of obtained for this reaction are almost exactly within small experimental error that value. Or if you were to do Hess's law, if you were given 2 or 3 equations that could be added up to this target equation, it would also come out minus 368 kilojoules. Either way will work. Okay, let's see. I'll be getting close to the end. Time for me to get up on my soapbox. Talk about forms of energy that power our economy, or the world economy for that matter. Fossil fuels. What do we mean by fossil fuels? Well, a fossil is something that's been preserved in the ground, right? We normally think of fossils as, say, bones that have been turned into stone, right? The minerals in the bone, the organics have been replaced by minerals. So we have fossilized bones are actually rock. Well, fossil fuels are those that have been stored in the ground also, like oil, petroleum products, natural gas, coal. Those are all fossil fuels. And by the way, the United States has more potential for fossil fuels that have not been tapped than any other place in the world. Now, of course, the Saudis and the Kuwaitis have easy access to petroleum products. because all you have to do is drill through sand and you hit their formations. Whereas in this country, it takes a little more technology to get at ours. Like fracking is one way to do it. We can go into old depleted oil fields and gas fields and frack them and probably get as much or more out of them after the fracking than we did before. Wood. Now, fossil fuels came along, probably in the early 20th century. Wood, traditionally for millennia, has been the choice for heating your domiciles, cooking your food, making weapons. Wood has been the choice because it was readily available, and they didn't know about fossil fuels at that time. I don't know of any cultures that did. There's also hydroelectric power, right? Or hydropower. It doesn't have to be electric. I mean, you can use water, the falling water in the gravity field, to power machines. And before we converted the difference in water levels into electricity, we converted into a mechanical form, like water wheels were used in the New England to power textile factories. And they just had to set up their factory next to a river and get it to turn that wheel. And then they had belts all over the place in their factory driving the machines. And I assume that was a definite hazard, right? You don't want to get close to one of those belts with loose clothing or hair. But then with the invention of electricity, there was a big war that went on between proponents of DC versus AC electricity. Edison, there it is. Edison was a big proponent of direct current. Problem with direct current was it wouldn't go very far. You couldn't get it to go more than a mile or two. And then you'd have to hook up to another new power station. And AC, alternating current, was developed by one of Edison's apprentices, Nikola Tesla. And Edison screwed Tesla out of a bonus that he had promised him if he did something, solve a problem. Solved the problem, and Edison reneged. So Tesla went to George Westinghouse, and they got together, and Tesla had ideas about how to make power go a long distance. And he knew from calculations that if you could up the voltage of the power, you could get it to go a long way, because that would decrease the current. And current traveling through a conductor is where you get power losses. High current means lots of power loss. So you want low current for long distances, and high voltage will get you there. And the technology of the day was easy to develop for converting low voltage AC current to high voltage AC current by magnetic induction. And that's another topic. That's physics, not chemistry. But there was a big battle that went on between Westinghouse and Tesla and Edison. And Edison was desperate. He even went so far as to electrocute elephants with AC current to try to fearmonger people into rejecting alternating current. Of course, nowadays, they probably lock him up for doing that. Anyway, fortunately, Westinghouse and Tesla won out, and their alternating current system was dominant for all of the 20th century and into now the 21st century. But there are technologies now that will take DC electricity and boost its voltage. And that eliminates some of the problems that were inherent to AC current. AC current, the direction of the current goes this way and then back that way. And in this country, it does that 60 cycles a second. Right? In Europe, it's 50. But when it does that, when you go this and stop and have to go back, you rob some of the power because you got to turn around and go back the other direction. But with DC current, once you get it going, you don't have to stop it. It just keeps going and you eliminate that loss. It's called impedance. So now we have the ability to up the voltage of direct current and send it great distances more efficiently. Also, AC current only requires the outer layer of your conductor. So the inner layer is just wasted. But you need a certain amount in order to get it to go. So you have to make your conductors big enough. And you just, the design of the conductor in these high power lines is a whole nother engineering feat. But with direct current, you can make your conductor big, and that just means that it can conduct more efficiently because DC current travels through the entire conductor. Okay, now to make a short story long, once we got hydroelectric power available, then we started building dams everywhere in the early part of the 20th century. And we've pretty much used up, in this country at least, all of our available water resources for hydroelectric power, because you need a certain distance from top to bottom to get enough force to drive the dynamos. Now you can, for local scales, small communities or individual homes, you can dam up water at this level and then run it down a pipe to an alternator at some level below and get electricity for your house. But for large scale base load electricity, we've used up all of our available hydroelectric sources. Then there's nuclear power. Nuclear power is simply extracting energy at this point from fission. Like we have fissile materials like U-235 is common. And to make peacetime use of U-235, you only need about 5% enrichment. It doesn't have to be better than 95% like you would need to make a bomb, right? So if you get that much enrichment, then you can use that enriched uranium in your nuclear reactor, and it will produce lots of heat and boil water that runs through a turbine that drives a dynamo, and there's your electricity. And the only pollution that you can derive from this is excess heat, right? You don't get any of the commonly labeled pollutants like carbon dioxide and those things. That's another topic. So nuclear power is a very environmentally friendly as compared to coal plants. There's no waste product. The only waste is heat. Wind and solar, we can produce electricity from wind and solar, right? On an individual scale, it's probably more efficient than trying to make large base load plants for supplying the electric grid. The problem with wind and solar is it's intermittent. Right? You may get wind for a while, or you may get, obviously, solar maximum 12 hours a day. Even in northern climates, even if you get more solar per day, a lot of it's absorbed in the atmosphere because because of the tilt of the earth. So wind and solar are not good base load candidates. And those environmentalists who propose switching entirely over to renewables like wind and solar are it's a pipe dream. It never happened. The only reason it's gone as far as it has is because of government subsidies. So I forget who said, if you want more of it, subsidize it. If you want less of it, tax it. So that's what they tried to do and failed. In fact, a lot of money that went into these, what Obama called shovel-ready projects, that money just evaporated. It went into companies, it just disappeared, or it went into companies that were around for 6 months and they went bankrupt. So you know that money was pocketed by somebody. Okay. All right. This is just showing, oh, I've already gone over the time. So if you have to leave, that's okay. In the mid to late 19th century, we were still using a lot of wood. And some places on the earth are denuded of forest because of that. I'm told that Spain used to be forest from coast to coast. But over the centuries, it's been turned into what looks like the Southwest US. That's why Sergio Leone made his spaghetti westerns over there, because it looked like the Western United States. So he made the Spain. And then another train of thought says that the king and queen of Spain cut down all their forests to make the Armada to go attack Britain. I don't know if that's true or not. Then by the turn of the 20th century, 1900s, we were starting to use more coal. And that's a direct result, I think, of the Industrial Revolution. Once we found this fossil fuel source that was readily available and easily obtained, well, not easy for the miner, but it's there and available. Then we started using coal instead. And by the middle of the 20th century, oil and gas was taking over because it was easier and safer to get. And by the late 20th century, it was dominant. It was only when the environmentalists started spouting their nonsense about carbon dioxide as a pollutant, that oil and gas started to decline somewhat. I mean, it depends on who you ask as to whether carbon dioxide is a problem compound, right? If you ask any green plant, you say, no, that's food, right? So I think the main driver for carbon dioxide as a problem compound is money. If you stand to gain money from it, you're gonna spout that doctrine. Okay, the Earth's atmosphere. Okay, now we're going to talk about global warming, right? It used to be called global warming. Actually, before that, it was called global cooling, right? When I was a kid, there was some fear among scientists that we were headed for another ice age, right? Never happened. So they changed their tune and went from global cooling to global warming. And then when global warming didn't pan out, they started calling it global climate change. Anthropogenic, that is man-caused global climate change. I mean, that is the height of hubris. That's a Greek term that means pride. To think that we can change the Earth's climate that drastically. There are other factors that are not even considered in the climate change models. In fact, all the models now fail. None of them work. And for various reasons, and I don't have time to go into it right now. But they keep trying to tweak them and make them work, and whenever they do, they fail again. So the idea is that the Earth's atmosphere is transparent to visible light. So it strikes the Earth and plants and whatever, but it's re-radiated at a longer wavelength, in the infrared usually. Well, there's certain compounds in the Earth's atmosphere that will reflect that infrared back to the Earth and keep that energy in the Earth's atmosphere. Carbon dioxide is absorber, right? Water is even less an absorber of infrared radiation. Methane is much more efficient at absorbing infrared radiation than carbon dioxide or water. But there's not a lot of methane in the atmosphere. There's not a lot of CO2 in the atmosphere either. It's only a little over 400 parts per million, right? But there is a ton of water in the Earth's atmosphere. So that is an extensive property. Even though it has less intrinsic absorption capacity, there's so much more of it that water is the dominant factor for energy absorption in the atmosphere. And then we throw in another can of worms. What form does water take in the atmosphere? Well, it could be water vapor, but it could be clouds too. And we know that clouds, the light coming from the sun doesn't even make it to the surface of the Earth. If there are clouds, it just reflects back into space. So it's a difficult problem. I'll admit that. It's extremely difficult. And when I say that, I'm also ready to say that any scientist who says he understands and makes chiseled in stone predictions is lying not just to me, to himself. They don't understand it well enough to make the predictions that they are making. Now, in the solar system, do we have a runaway greenhouse effect somewhere? Oh yeah, Venus. Venus, the surface of Venus is hot enough to melt lead. And it's largely due to, well, two things. One is the greenhouse effect, which is not so much, there's carbon dioxide there, and a lot of it, but there's also sulfur dioxide, which is a more efficient absorber than carbon dioxide. But it's also half the distance that we are to the sun. So it gets 4 times as much radiation. So Venus, yeah, Venus is a good example of a runaway greenhouse effect, but we didn't cause it. And we're not causing it on the Earth either. All right, so this is somebody's idea of science. This picture. Now, what do we do about energy sources? Well, it's been estimated that we have enough coal in the ground in this country to fuel our economy for another 200 or 300 years. So there's time. What we ought to do is let the market decide what energy we should be using. Coal conversion, gasification, removes a lot of the ash and the potential polluters from coal. And when you burn gas, it produces only carbon dioxide and water. So that's one possibility. Hydrogen as a fuel. That's the holy grail of chemical reaction fuels, is hydrogen. Because all you need is water and direct current to split the water molecule into hydrogen and oxygen. You can let the oxygen go if you want, keep the hydrogen, and use that as a fuel. The limiting factor in producing hydrogen that way is cheap energy. You need a cheap energy form, non-polluting, in order to split the water molecule. And the best candidate for that now is nuclear power. So I tell my students, if you get face to face with a rabid environmentalist and they start spouting all this stuff, ask them what their position is on nuclear power. Right? If they say this pollutes that and this pollutes that, say, all right, what do you think about nuclear power? If they're against nuclear power, then they're lying to themselves and to you, because nuclear power is the way to go if you want none of those pollutants. So we can either use hydrogen for internal combustion engines, easily modified, or fuel cells. Right? Fuel cell technology is getting there. It's not quite there yet, for mass production and consumption. Energy alternatives. Well, oil shale for fracking, right? We can get tons of that stuff. It's still underground, and all we have to do is drill horizontal wells. They go down, and then they turn the well. It goes that way, and it goes for miles. And then they go in there and they just pump drilling mud of a certain consistency at extremely high pressures, and it goes through the holes in the pipe and into the rock and just cracks it. And then the oil comes flowing out. Natural gas, same way. In fact, it's even easier. Once you frack it, it just comes spewing out of the rock. Ethanol production. The problem with ethanol from, in this country, it's primarily from corn, is it costs more to produce a gallon of ethanol than it would to just sell the grain that's required to make the ethanol. So if it were not for government subsidies, the ethanol from corn industry would collapse overnight. It's not economically viable. Methanol is another alcohol that can be produced from biomass. I don't know too much about that. Seed oil, you can get oils from various seeds. Solar, that has numerous problems. One is intermittent availability. We talked about that already. That's why you need batteries. Inefficient storage technologies, we're tackling that. I don't think we're quite there yet because those batteries do have a limited life. Economics, right? Without government subsidies, it would go away too. So are you getting a tax break for doing this?
I will be.
Yeah, you should be. Yes. Yeah. And then there are the environmental hazards. These photovoltaic cells are made from rare earth elements, and they're not that concentrated. They're more concentrated in some spots than others. China has a huge deposit. Ukraine has lots of them. There are parts of South America that are loaded with lithium. But to extract them creates environmental hazards with the waste materials. Okay, so we got to deal with that. And then once your photovoltaic cells have run their course and they're not efficient anymore, right? They have a limited life, then you got to get rid of them, right? And they still have those hazardous elements inside. So you gotta find a way to process them. And I don't mean send them to India so 5- and 6-year-old kids can rummage through there and pick out the parts. So there are environmental hazards going in and coming out. And then nuclear. Nuclear solves all of these problems. And there are various technologies for nuclear power that don't rely on those that are hazards from the past, like the pressurized water reactors, like the one at 3 Mile Island where we had that accident decades ago. They've got more efficient reactors now, and you can make them smaller, modular nuclear reactors that can power a small community. So with smaller amounts of nuclear material inside, the risk is much smaller. There are even companies that put nuclear reactors on barges or ships, and they rent them out to communities, right? If this community next to a river wants more power, well, even for a limited period of time, they just move that barge up there and hook it up to their grid, and they're ready to roll. Okay.